package lead for the Hybrid GEOTABS project, and welcome to our second webinar training session, Designing Hybrid GEOTABS Comfort Supplied in a Sustainable Way. There will be 5 talks by members of our consortium from practice and academia, followed by a question and answer session at the end. This training will be about 2.5 hours long, including a short break in the middle of the training talks. As a matter of housekeeping, this webinar will be recorded, just to let you know, and the slides of all the talks today will be made available on our website within the publications and presentations area of the website. All attendees are muted by default, and there should apparently, it will look like there's only you attending, but there's about 90 to 100 people signed up to join this webinar. Please use the Q&A section to send your questions to everyone, but not in private, so that we can see the questions, and we will collate these and answer them at the end of the session. We'd like to open the questions to the group then and direct to the appropriate speaker. So without further ado, to start our training, talking about the Hybrid GEOTABS concept and project, Dr. Aline Himp will be presenting. She is a postdoctoral researcher at Ghent University, Building Physics Research Group, and the Hybrid GEOTABS project manager.
Good morning. Can you see my presentation?
Yes, it's great.
Thank you, Freedom. So, good morning. Hybrid GEOTABS is the name of an HVAC concept, as well as a European Horizon 2020 project. In this introductory session, I will introduce both the concept and the project to you. So what is Hybrid GEOTABS? Hybrid GEOTABS starts from the GEOTABS concept, which is the core of this HVAC solution. GEOTABS refers to the combination of a thermally activated building system, such as concrete core activation, with the use of shallow geothermal energy, which may be upgraded using a heat pump. So that is GEOTABS. HABS is an example of a radiant heating and or cooling system. This sort of systems provide sensible heating and cooling for emitting the sensible heating and cooling to the rooms, in which more than 50% of the heat transfer happens via radiation. Such systems are well known for their very high thermal comfort and indoor environmental quality. Some advantages in terms of comfort are the uniform temperature distribution, the minimization of the risk of drought when compared to all-air systems, a quiet operation, and because the system is integrated in the building, also an increased room height and flexibility of space are well-known benefits. So in this sort of system, the tubes that are distributing the heat to the rooms are embedded within the floors, walls, or ceilings. Specifically for thermally activated building systems, they are really in the core of the concrete floors, as you see in the example below. So the pipes are embedded within the core of the concrete, making that when we supply heat or cold throughout the tubes, that the entire core or the entire thermal mass of this floor can be activated. It becomes warmer or colder. So this high thermal inertia of this emission system allows to make a short-term energy storage as a daily time frame, which allows to shift the loads between the moment there is a demand and the moment there is a supply, further leading to some nice benefits, such as the option of peak shaving and flexibility towards smart grid. Because also this system uses very large emission surfaces, very low temperature heating and very high temperature cooling at temperatures extremely close to comfort temperatures are possible to use, which also leads to a self-regulating effect of taps. An example of how such systems look in the interior, typically they are integrated in the floors and or the ceilings of the buildings. On the other hand, we have the geothermal energy, which is a renewable and zero carbon energy source. It is available at rather low temperatures, around 10 degrees in Central Europe. Of course, this may vary according to the location where you are, and has a very high storage capacity. Both these elements allow to use the underground as a seasonal energy storage, in which during summertime, the heat that is too much available in the building can be stored into the underground, and in wintertime, it can be used to heat up the building. So the temperatures that we need within the taps and the temperatures available in the geothermal source are quite close to each other. And this small temperature difference is actually a great benefit for the use of heat pumps, which can work with very high efficiency. Moreover, at moments that the temperature in the underground is lower than the temperature required for cooling, we can directly use the temperature from the underground to cool down the building, which we call passive cooling. So in general, the combination of geothermal and taps allows a very high energy efficiency of the HVAC system throughout the whole year. That is why we believe every building deserves a share of GEOTABS. A share of GEOTABS, as I mentioned, because there are also some reasons to look into combining the GEOTABS system with additional sources. One being the moments that there are very sudden heating or cooling demands in the building within very short periods of time, where the taps is a bit too slow to react. For example, when the sun hits a heavily glazed building. On the other hand, also in terms of feasibility, it might be interesting to look at secondary sources on the geothermal side for technical feasibility, but also for financial reasons. It may be more interesting to combine them with a secondary source. So that's why we go to a hybrid GEOTABS system, which combines the taps with a fast reacting emission system. This can simply be the air handling unit which pre-cools or preheats the air when that is needed, but could also be other emission systems. And on the source side, geothermal may be combined with something as simple and as cheap as a gas boiler, but also offers the opportunity to be combined with other renewable energy sources, increasing the sustainability options. So in general, the hybrid solution allows to broaden the applicability of GEOTABS and also make it more sustainable. Even more sustainable. In order to make sure that these different systems work together in an efficient way, that we use a model predictive control, which is an advanced type of controller that really integrates the cooperation of the different parts of the system and optimizes their energy efficiency, comfort, and costs. So, this combination of GEOTABS with secondary systems and model predictive control is what we call the hybrid GEOTABS concept. Of course, when the concept is set, there were still a lot of questions. One of them being the central question of our session today, that is how to design hybrid GEOTABS. Other questions were related to the development of model predictive controls, to the assessment of which energy savings can be realized in reality, how good is the comfort when we apply these systems in buildings, what is its cost, and how do we bring this system to the market? How can we provide better materials to assist people wanting to use this system and to increase its commercial attractiveness? This is how the Hybrid GEOTABS project came to start. It's a Horizon 2020 EU project, which is called Model Predictive Control and Innovative System Integration of GEOTABS in Hybrid Low-Grade Thermal Energy Systems, which is about to end in about 2 months from now. The Hybrid GEOTABS team is a consortium, consists of people from small and medium-sized enterprises, industry, academia, and dissemination partners, all together working on this multidisciplinary challenge that we have to bring Hybrid GEOTABS to you. The consortium exists of, so the small and medium-sized enterprises are Studiebureau Boydens Engineering from Belgium, Lemon Consult Engineering from Switzerland, GEOthermal Energy from Spain. We also have Energo Cluster from the Czech Republic. The industry partners are Uponor and Visma. The academic partners are Ghent University as coordinator of this project, KU Leuven, Leuven University, also located in Belgium, DTU, Danish Technical University, and Maastricht University. Finally, we work together with REVA, the Federation of European HVAC, and associations and climate futures for dissemination purposes. So the goals of the project are to optimize, demonstrate, and exploit this concept. I'm not going to go through the details of each of these elements today. Of course, regarding the optimization, you will hear much more about how to design Hybrid GEOTABS. Our main challenge there is to optimize the sizing of the key components in the Hybrid GEOTABS systems so that you can use this method to assess the feasibility of Hybrid GEOTABS already in feasibility study and pre-design. We developed some easy-to-use or rather easy-to-use tools for you that allow you to come to a quick assessment of the feasibility of this system and therefore also reduce the costs for the engineers in pre-design phase. I will, to finish my presentation, I will have a look with you into the results of our demonstration activities very shortly. So we have been looking into a number of case study buildings. The project mainly focused on buildings with higher than 1,000 square meter size, so mid-size and large-scale buildings, focusing on the typologies of offices, schools, multi-family buildings, and elderly homes. And we have been looking throughout the EU climates. Our demonstration and case study buildings were 2 office buildings, one in Luxembourg, one in Belgium, an elderly home in Belgium, a school in Czech Republic, and a multi-family building in Switzerland, in which the technologies were demonstrated, validated, and of which you can find much more results on our website. Some of the key performance indicators or the key performances of the Hybrid GEOTABS concept that were assessed were the indoor environmental quality. So we know, we measured, we tested, and so that there's very high thermal comfort and indoor environmental quality possible with this system. These are the results of one of our case study buildings, indicating very high comfort categories and also very high CO2 indoor air quality categories that have been observed. Secondly, in terms of the environmental performance, we have seen CO2 savings higher than 50% compared to standard non-renewable energy systems, and that includes only the benefit of the GEOTABS itself, so not the benefits that can be additionally added by improving the renewable energies, by adding other renewable energy sources to the system. In terms of energy performance, about 30% of energy savings are possible in Hybrid GEOTABS systems thanks to the use of model predictive controls. And in terms of costs, we estimate that when comparing to a standard non-renewable installation with a gas boiler in a building, we estimate life cycle cost increases of about 1 to 5%. But of course, in this case, we have also all the environmental benefits. So these are the main performance results we achieved with the testing on validating the Hybrid GEOTABS concept, making it quite an interesting system to use. And with this, I will finish my introduction and give the word to the next partners who are going to talk more about design solutions. Thank you.
Thank you, Eline. We're now going to hear from Professor Wim Boydens. Wim is Chief Scientific and Technology Officer of Boydens Engineering and Professor at Ghent University for 20 years. He's a design engineer of almost 30 years in the field of energy and technology in buildings and districts. Boydens has grown from 10 to 150 and are operational in Europe and Southeast Asia. He is active in the field in education and research and in societal and technical national associations. And his mission and dedication is to integrate sustainability in innovative building and district designs.
Wim, can you share your screen? I unmuted you.
One second.
That's great. Presenter, yeah.
That's almost great. I'll start from the beginning. I think that's better. So good morning, everybody from my side. What I want to dig into with you, as I believe a lot of you are active in designing, and designing is not just being there in the early stage and making some drawings, but designing is about following up the works, how the installers do it, how the control engineers in the end try to get the building operational, and after all, when the client afterwards has concerns or questions, being there. So designers are a word for somebody who really takes care of the building from scratch to full operation. So I would like to go through the design challenges with you, and also elaborate further how we provided solutions for those challenges in implementation of GEOTABS in hybrid GEOTABS concepts. So we're starting a little bit from lessons learned, because we have been busy, most of the people in the consortium, for about 20 and some 30 years with GEOTABS. So we started really from field expertise and research expertise. And where we come to solve those challenges is also a little bit illustrated by the upper picture there, like the way of how we work, how we approach a concept to design it properly. It's really redefining our approach. Just Eline showed you who was involved in the project in the whole, but here I just focus a little bit on the ones who are really involved in design. You can see on the upper part of the page, and the involved industries. Is it control? Is it about the heat pump? Is it about the taps and the ground source? You can see them on the underside of the slide. Okay, so you understand now by the explanation of Eline what GEOTABS is and what hybrid GEOTABS is. So how do we evaluate it from a designer's point of view? And first, maybe it's a little bit rephrasing the strong points. Most of them Eline brought forward already. But one thing that is very nice to have is that it is a logic concept to explain to your client. It looks simple, let's state it as such, that you really have an easy to show concept with the ground source, with the taps, and then you have a heat pump in the middle, and you have a normal, not very rocket science heat exchanger above it, where the one operation active in winter time heats up the building, and a very passive and low cost operation heat exchanger cools down the building by connecting the taps with the ground source heat pump. So logic to explain, you need 2 sentences or 3 sentences, And if you're somebody who can really enthusiasm your client, then probably he will be triggered and will say, wow, you are a really creative engineer. You can talk also about seasonal storage element, which is very relevant in our energy transition. So how do we move the heat from summer to use it in the wintertime? So this is involved in the concept. We have a very attractive feature that is the passive cooling mode. We can use it almost everywhere in Europe. Of course, if you go to the extreme south, this becomes a challenge. There you have higher ground temperatures. And of course, the load on the building is mainly cooling. So that means that the passive cooling mode there is not that much used as in Central and Northern Europe. It has an integrated share of renewables, renewable heat. So that means actually within the concept already, you normally, the most legislations and EPBD frames in Europe, they ask a percentage, a minimum percentage of renewables in each building. So it means that you already comply with that simply by adding or using the hybrid GEOTABS. And on top of that, it's upgradable. So if you design a building now and it becomes or it comes into operation in about 2 or 3 years, even if the European frame lifts up the demands and asks for a higher share of renewable in your building, then you still have the roof. You can still add wind turbines. You can add solar panels, be it thermal or be it photovoltaic. So it's really a future-proof concept that you're bringing forward to your client. He will always be happy to hear that, because then his investment is secure for many decades to come. On the environmental side, you have no local emissions. So you have no fumes, exhaust. You do not need a chimney. You also have less constraints on the safety and security side in your building when you don't apply or implement a combustion solution. So it are all features that are very nice in a first talk with your client, and he will be pleased of having met you for his project. If you look at the system itself, Elin already mentioned, you work a lot on radiation on the emission side. So that means that's a high comfort. You have a uniform temperature distribution and you have no draft. On top of that, you have the self-regulating effect. It's a little bit more difficult to assess just by standard methods. But obviously, short explanation, if you have a concrete slab, a big inertia of heat or cold, at a certain temperature close to the room temperature, let's say 2 to 3 degrees. So if your room temperature is 24, then your slab has a surface temperature of about 21. If the loads increase, the sun pops up and the temperature rises slightly in the room, then the delta T between the slab and the room increases as well, of course. And that means immediately that you have an increase of the emission from the slab to the room. So it is really regulating, controlling, but more in the managing way, the gliding of the temperature upwards or downwards. And on top of that, because you have the concrete slab, there's a lot of heat or cold stored in that, so it can cope with an additional load excess or excess load for quite a long time. Let's say we're talking about days here. The comfort is very robust. So it means even if you have a power down situation, if your heat pump has a problem and pops out, you will not feel it in the comfort for a day or more. And it's very flexible. Elin already mentioned, you can choose actually when you load the thermal energy in the slab, because the emission will occur 5 to 12 hours later. So you have an enormous flexibility, and you can work on, for example, variable electricity prices that the grid will offer in the future. In some countries, they already do. You have no installation noise. Elin talked about that enough, and no draft risk, or no more draft risk than needed. And what is quite important to understand too is that you have a very low maintenance cost. Normally in European standards, maintenance costs are related to the investment cost. We all know those tables where you see a percentage of 5 or 3, depending on what component you have. Now, if you look at the GEOTABS system, where is the biggest investment? It's the pipes and the slabs. That's not such a big investment. But then you have the drilling, so the geothermal borehole field, and that is quite an investment. But if you look at the maintenance side, it's just tubes embedded in the ground or in the concrete. And if they are embedded properly, if you have a good quality frame for the installers to do so, then it is not asking any maintenance. It's only the heat pump, which is a smaller component, that has a logic periodic maintenance issue, but actually not much more than you would have for a gas boiler or a chiller. The lifespan, therefore, and then mainly for the biggest part of the investment, is enormously long. It's embedded, it's safe, so it's actually a lifespan similar to the building. And so the concrete core activation and the ground source is really something, a long-term investment. The freedom of space and height, we already mentioned it, or Eline did. The height, for example, if you have a high-rise building with about 15 floors, and you would calculate what the normal height would be that you need, in that same height, if you use the hybridGEOTABS concept, you can add 2 more floors. So also for investors, this is quite interesting. So a lot of strong points, I would say. But a lot of strong points, still we see in the past 20 years that the deployment of the concept in the market goes slow. And then we of course wonder, why is that? I would like to go through them because it's actually those challenges that we try to overcome in our hybridGEOTABS project. One of the first to notice is that we have a very intensive early design phase. We have a concept that is easy to explain, but if somebody asks you, and will this provide me the comfort I need? You talk about the self-regulating effect. You talk about stored energy. Can you show me, can you assure me of the fact that my building will be comfortable? So if you want to show that to your client, then you really have the challenge. You didn't even convince him of using it, just triggering him that it's important and that it's nice and that it's environmentally friendly, and that it will provide what he needs. But if you want to prove that, you have to dig into simulation in a very early phase of the project. So that means a lot of burden, a lot of costs, and you're not even sure that after the pre-design phase, the client will say, okay, we'll go for this project or this concept within your task. So this is a barrier that is very important, and it's mainly on the side of the designer. So that is what we want to solve, surely. Another one, it's a little bit related to it, is that you need to look at the ground balance. If you extract more heat in winter or far more heat in winter than you supply again in summer to the ground, then the temperature of the ground will go downwards. If it's the other way around, if it's a cooling dominated building, the temperature in the underground will rise. So it means on the long term, you have to also look at the nice phrase of the concept will still work within 10, 15, 20, 30 years. So you should look at the balance between the heating demands and the cooling demands. And then, of course, you have an interaction with the building design. Is the building fitting in this balance consideration? And if you want to know that, then again, you have to try to make a good assessment of the cooling loads, of the heating loads, and you have to do a kind of simulation, what we mainly could do with EED. That's a ground assessment software, where you can see, will the temperature go down, will it go up? And if it goes up or down, should not be necessarily a problem, as long as the temperatures in winter and summer are still the ones we look at to have the high performance operation of the system. But it's a burden for the designer. You have to do additional work. A last part is the impact of control. And what I mean by that, this is typically a system, and even on multiple sites, that combines storage of thermal energy with instant supply of heat and cold by the heat pump. So that means actually, and probably you all know it from the design question or the sizing question of domestic hot water systems, that you have a liberty of increasing the storage or downsizing the storage and then giving a little bit more power on the supply side on the heat pump. So we have a lot of possibilities, and it's quite an issue like, what will I do? What is cost optimal? That could be one. But also, how is it controlled in the end? If you use a lot of storage, but the control of the loading of the storage is not done properly, you could have a problem in the end. So how you control the system in operation could have an impact on how you should size it. We go a little bit further with challenges. I hope you're not now already demotivated about the concept, but I don't think so, because you all look like dedicated engineers and designers. Another challenge is individual room set points. If you have the slabs, the taps, doing the thermal job, then of course it's not that easy to have two neighboring rooms asking different set points. So that means if the user comes in the room and he wants to put the temperature a little bit higher, of course the taps will not have a reaction time that can provide it within a reasonable time. Another one is the design of the borehole field. Already Elin mentioned, it's very investment intensive. So we should look at cost optimality. It does not really make sense to try to match with the extreme peaks in summer and winter with the borehole field. Not always, because sometimes this creates a cost that is not proportional to what you want to achieve. So this is a huge question. How do I do that? And the last thing is a fair comparison. We see there's a lot of advantages, a lot of nice points, easy to sell, but how do we compare it fairly with other competing concepts? And not only price-based. This is rather straightforward, still a lot of work, but how do we compare it with regard to the environmental impact that this concept has, and that's fairly tempered and perfect in the energy transition that we are in. But we have to compare it to other solutions that have a lot of more damage or pollution towards the environment. Okay, a big challenge also, and it's mainly for Belgium, you see on the right side picture or graph, that is the gap between the price you pay for a kilowatt hour energy that is brought to the building by the electrical grid, and the same kilowatt hour of energy that is brought by, for example, gas. And if you look at Belgium, you see that we have a gap there of a factor 4.5. Germany is also having a huge factor. So that means that our concept with the heat pump base should operate really very good at high SPFs, at high COPs, enabled to have an operational advantage towards those more fossil, not more fossil, pure fossil systems that logically are not future-proof. But on the other hand, the prices of today do not encourage our client to choose for the more low-carbon systems. So we should try to create more evidence of common sense. Good. We still have other challenges. I'll go a little bit more quickly so that we have time for solutions as well. And one of them is fine-tuning of control. We have a slow reacting system, the taps. It has the self-regulating effect, but still to find the right heating curves, the right cooling curves for the setup of the control, you need dynamic thinking. You need to look at graphs, and this is quite an expert task and takes a long time. So an effort for the designer again. We should solve this. on the whole, if you look at the components, they're all proven solutions. There's no more challenges for how do we drill in the ground and then how do we put the pipe in it. Actually, you could say there are already good quality frames to have that handled. But still, we see that it's new for installers and control firms. They are not really into it yet. That means that, again, the designer has to do an intensive supervision in order not to let mistakes happen during the construction phase. Optimizing energy use is also a challenge. The comfort is very robust. It's easy to provide the comfort, but if you want to see if it's running smoothly and energy optimal, then you have to dig in deeper. So that means the commissioning is harder. The changing from the cooling to the heating mode, Eileen explained. It's choosing when do I change from a cold slab to a warm slab and vice versa. So that is also something that is not easy to do if you don't use artificial intelligence that can grasp this exercise much more precisely than we can do with our human thinking. Room acoustics was a problem from the past for tabs, for concrete core activation, and I just integrated or inserted some solutions that already are in the market in the pictures. Good. Then we look further. How do we solve this problem? Eileen explained already. We have a hybrid GEOTABS, and hybrid GEOTABS consists of 3 elements, and one element, of course, is the GEOTABS. We know it already now. But then we have the secondary emission system and the secondary supply system. Together we call this the secondary system. It should be faster. It should be cheaper. And if it's less environmental friendly, okay, we can live with it as long as we put the largest share of energy use on the primary system, being the GEOTABS. So it's really a kind of a helping system that only should work when it's really needed. And how do we do that? With the third element of the hybrid GEOTABS is with the MPC, or the model predictive control. That should guard the operation of the system, that the secondary system should not work when it is not needed, should anticipate also, and should put the most energy supply on the primary system. Good, so we can put this into schemes, and this is a scheme that probably most designers are well familiar with, where we see the yellow and the under elements being the GEOTABS elements. You can see the borer heat exchanger, the heat exchanger, the heat pump connected to the tabs, and we can change from cooling to heating. And then above that, we see a divided system with more conventional, classical supply systems like the chiller and the gas boiler. But in the future, it could be not only in the future, today already, this could be replaced by an air-to-water heat pump. It could be replaced by a district heating cooling system that can be or act as a secondary supply. And then it's combined with some emission system, could be fan coil units, could be coils in the air handling room by room, because we have ventilation anyway for indoor air quality. So it means that actually the secondary system could be really cost efficient and just being there to help overcome the challenges of the most performance-based system being the GEOTABS. We go to a little bit more combinations because we have other considerations, and I give them to you, but I will also refer to what you see, the link there to the hydraulic schemes on the website of our hybrid GEOTABS project, is where we look, okay, we have hybrid system, we have a choice. If you have district heating or cooling, you can integrate it. If you have something with biomass, you can integrate it. So we made up a lot of hydronic schemes, generic ones, to be able not to spend too much time for the installer and for the designer to put it up. 2 issues that you should be aware about, not the problem, but the issue of domestic hot water with higher temperature levels. So this is also integrated in some schemes. How do you solve that? And then secondly, the regeneration of the ground. If you don't have a balance because your building is really not having a comparable heating and cooling demand over a year, well, then you could have other solutions like solar thermal panels to regenerate or cooling tower to regenerate in a very efficient way and environmentally friendly way your borehole field. Okay, so if we go hybrid, if we add that second system, what have we solved then? We have solved the issue of the interaction with the building design. The building does not have to be perfectly balanced regarding heating loads or heating demands and cooling demands. We can put the balanced part on the ground, and we can put the leftover, let's say, to the secondary emission system. The individual room set points by adding the secondary system are also solved. If the director comes in and the director of the company wants a little bit a hotter temperature in his room, he can just activate the thermostat and the secondary emission system will react to that. But the taps will still remain to provide the largest share of heat to the building. The cost optimality as well. The peaks in wintertime, they cost a lot of money. If we put them purely on the geothermal system, okay, we'll take this up those few hours with the secondary. And we see that providing generic schemes helps out installers, helps control firms to not make the first mistakes each time again and again. So this helps out designers in really choosing for the system to offer it to their clients. Now, what is MPC? It is part of hybridGEOTABS as a concept, model predictive control. Eileen tried already to give you an idea about what it is. It is actually using a model of the building plus the system plus the user. You make a model of it, and with that model, you try to assess what will happen if you take certain control actions. And the MPC does that time and time and time again. I think Damien Picard will give you some more insights in that. And it also uses the weather predictions. So it knows what is coming up, and it's looking for the best actions to take now in order to have a good result. And a good result, the comfort is not the big issue. It is, of course, important, but it's easy to achieve. But we want to achieve this comfort by a cost that is as low as possible and with an environmental cost that is as low as possible. So actually, you're using an objective function to tell your control what it should look at. That's mainly elaborated at the KU Leuven. That's Professor Lieverhelsen and her research group Thermal System Simulation. Damien from the group of Lieverhelsen will go more into detail how this system comes to market, jumps to market. And then I wanted to tell you also what challenges are met by this MPC solution. The impact of control. We have a model. We can integrate how it is controlled, of course, because it does this in operation. So there's room for sizing our systems, knowing how performant the control will be. This is actually something that we do already now, but towards practice of design, this is the next step. This will evolve in the coming 5 years enormously, because it's a direct impact also on investment cost. Another thing is the fine-tuning of control. If we have a model predictive control, which actually is an artificial intelligence using a model of the building to know what to do, this will enable us to have the smooth commissioning. We don't have to look at graphs and trends and logs. No, the MPC does it for us and optimizes the operation of the whole. And then next thing, and it's very close to the former one, if the comfort is well, but the energy use can be optimized, being more clean or being less in volume, then also the MPC will take this up. So it's not a task for the designer anymore. So wrapping up a little bit, because we didn't design anything yet, maybe rephrase. We have slabs in almost every building. If we put tubes in that slabs, we have taps. If we connect it to a geothermal system, which can be used everywhere. then why should we not see GEOTABS as a building component, as an inherent part of the building construction? And then just say we have slabs, we use them, we activate them, we connect them to the geothermal system. Good, then we know how much slabs we have, of course, because that's the building who determines that. But then the question is, okay, if I put this, what will the building do? How can I mimic the behavior of the building in a very early design phase? Because out of that behavior, I want to assess the performance. What would those taps or those slabs deliver to my building? And what is still needed from a secondary system? If we have a secondary emission system, we don't want to make it too big. And how do they collaborate? Those are the main questions. And what is the total cost of ownership? Is it competitive? And environmentally, does it meet and in how far the requirements that we have in this energy transition? So we actually want to compare different concepts, but on a fair level playing field, not only looking at investment cost, not only looking at investment cost and operation cost, but also looking towards the future and the CO2 emission and the price that will be implemented on what your building still provides as CO2 emission. So actually, the tool that we are putting together is a very big step. That's why we call it hybridGEOTABS tool 1.0 on solving this challenge. What we actually do, and Professor Laverge will go further into it, is the early design of the building. We try to grasp characteristics and out of a big pre-simulated database, grasp a building that comes near to it. So actually you're looking for a brother of your building that you have on the table, or you let the tool search for a brother, and that gives you quite a good idea in that early phase, what can I expect? And also, what does the GEOTABS part then deliver to the building? That's mainly also work from Ghent University, and Professor Laverge will explain. It's actually splitting up the slow system and the fast system. And what TCO analysis is concerned, environmental analysis, there, and Pascal Simons will go further on that after the break. There we use feedback from practice, cost relation curves from real designs, and also, of course, we implement the standards, for example, on CO2 emission factors that we have to use. So actually, we're coming to a tool that's easy to use in an early phase of the project and trying to cope with the challenge of the intensity of design in a very smooth way. And adapted to that early phase, we're not making a design for you all, but we're giving you a tool that very fast you can compare the concept to other concepts, mainly the conventional concepts for the 1.0 version, and that you can go to the client and really show what are the advantages, and not just having to talk and to dream and to convince, but actually putting something on the table that is based on a combination of research work and practitioners' expertise. Good, and we have as such solved all those challenges. So rephrase a little bit. About 20 years ago, Professor Bjarne Olesen started in industry and research with looking at GEOTABS. Then Professor Lievehelsen about 10 years ago had an important project on going towards more optimality of the GEOTABS pure system. And now, the last 4 years, we have been working to integrate that pure system in a hybrid system and make the operation and the control more performant, and bringing it to the design table in a way that it's feasible for you to make the choice to go for it. It's really a project for the last 4 years that really had a hand-in-hand research and practice collaboration. Very important. It's not first the one and then the other. It was really working together, of course, very intensively towards an outcome. We have a novel approach. We are using databases, pre-simulated databases, databases out of a practitioner experience, and artificial intelligence on top of that. The result is that we are really optimizing costs of the installation and building, that we are really decreasing, or we are able to assess the improvement of the environmental impact, and that's for you most important, we are decreasing the effort you have to do to put this sustainable project concept on the table. But the work is not all done, of course. It's a 1.0 version. So we are opening for the moment a knowledge center that all the challenges that we still have from this 1.0 version towards broadening and enriching the methods are going to be pursued in the future. So if anybody wants to step in after this project in this knowledge center, please let us know. You've seen that simulation is a miracle and a burden. It's a burden because it takes a lot of time. It's a big cost. It's not acknowledged yet by our end clients, but it still is the way to go to improve the behavior and the designs of our buildings. So I would like to invite you, and we will have some sessions too at the International Building Performance Simulation Conference, Building Simulation 2021 in Bruges. That's in September. And we'll all should look at the fact that our behavior kills the virus, of course, but we stand tall and we are sure that we can make a good cooperation platform there in September for you all. So all welcome, and I will give over to the next presenters.
Thank you very much, Wim. I'll now introduce Professor Jelle Leverge, and he's talking about hybrid GEOTABS design methodology. Jelle is an associate professor at Ghent University, Building Physics Research Group, and the hybrid GEOTABS project coordinator.
Hello, everyone. So I hope you're able to see my presentation now.
Yes.
Perfect. Okay. So the goal is for me to elaborate a bit on the actual design method and design tool and the background of the tool. I will mainly go over some of the things that were already introduced by Eline and Wim, and then elaborate on how we used those or addressed those issues in the tool. So first of all, the whole idea is to answer these two main questions: how to estimate the design power of the different components of the hybrid GEOTABS system, and estimate the energy flows, the yearly energy needed for the different components in the system in early design stages. As Eline already showed quite nicely, there are lots of advantages to the GEOTABS system, which is really the core of the hybrid GEOTABS concept, and that we are trying to give as much priority as possible, because due to its low temperature heating, high temperature cooling, and relatively high temperature source, which is then the ground, that's available compared to the outdoor environment, there's a potential for very high efficiency use of a geothermal heat pump. Of course, this geothermal heat exchanger also includes the potential for seasonal storage, optimizing the energy use or the differential between energy use for heating and cooling of the building across the different seasons. That was already mentioned also by Wim. And there is the self-regulating effect of the slabs that can be used for short-term energy storage in the building. So that provides flexibility, for example, to a smart grid. So that there are all kinds of advantages. They have been introduced quite extensively already. However, these also provide some challenges, because due to the fact that the system really operates best when it is combined into a hybrid system, as Wim mentioned, it becomes a relatively complex system to design. There's different components that each need to be sized and needs to be assessed in an early design stage to be able to advise clients. And of course, one of the advantages, namely that it's building integrated, which reduces the maintenance costs, is also a challenge for the design, because it means that the decision to take or to go for GEOTABS really needs to be taken very early in the design stage, because it needs to be integrated in the planning of the structure of the building. So for a design method, this really creates a challenging situation where there is very few actual information available on the planned project, and still to convince a client you need a reasonable estimate for costs and benefits in those early design stages, because that's the moment where the decisions need to be taken. I say a reasonable estimate because, of course, it doesn't need to be extremely detailed, but also, as was stated by Wim, it needs to be reasonably accurate in order to be able to do a fair comparison between other alternative systems. And so, for our design methods, what we really want out of it is that we are able to answer the question, what share of the total heating and cooling load will be covered by the GEOTABS, and so as a result of that, what size will the main components of the hybrid system have, and further related to that, what is a reasonable cost estimate for the complete system, and how will that translate into benefits, and so what is typical performance that we can estimate of this system once it is operational. To achieve that, there are some additional difficulties that we need to address, namely that a GEOTABS system is not as straightforward to design for as more conventional systems, exactly because of the same properties that also produce its benefits, namely the very high time constants of the emission system, which are typically more than a day long, and of course the constraints of the geothermal heat exchanger that we want to preserve in terms of temperature over a very long time period. As was already mentioned, the MPC is really the solution that in operational terms will integrate all of these different components and overcome the issue with adequate control for the time constant. However, it does not straightforward translate into how to design for it, because that means we will need to be able to take into consideration during the design process the fact that the system will be adequately controlled by the MPC. So really, we try to answer three questions. First of all, what are critical conditions for design that are associated with this type of hybrid system? It's not self-evident that these are the same conditions as we traditionally take. Traditionally, we design for peak cooling and peak heating demand. However, because two systems need to interact, the most critical condition for each of the components is not necessarily the critical condition for the whole system together. Second point is that we want to avoid to need to resort to very detailed simulations in early design stages, because they are prohibitively expensive at that point. we want to postpone that more detailed analysis, preferably to later stages in the design process, and still end up with a reasonably accurate estimate of cost and performance. And to be able to do that, we still need to be able to take into account the fact that there will be advanced controls taking care of the possible conflicts between the different components. So how do we solve this? We, in essence, use two simplifications or approaches that change the traditional design process. The first one is, as Wim already mentioned, we are, instead of making a case-by-case detailed simulation for every design, we resort to a big data approach where we use pre-calculated archetypes for a similar building as the one that is being designed in order to provide a good estimate at that point, and then can proceed with that for further detailed simulation later in the process. So this database approach is implemented in a web tool that will be introduced and more further discussed in the presentation after the break by Pascal. I'm just going to discuss the background of the tool. So what the tool mainly does is trying to automate and replace some of the more labor-intensive steps in a relatively detailed design process so that it can be effortlessly applied in early design stages. What it does is it takes a number of high-level building properties, and based on these high-level building properties, it selects from a pool of pre-calculated buildings an ideal heating and cooling curve for that system, then applies what we call a splitting algorithm, which I'll discuss later, on that to assign part of the load to the GEOTABS system and another part to the secondary system. And based on those splitted load profiles, we can then proceed to size the different components for the taps and the secondary system, and then provide that as feedback to the designer for informing the decision making about the selection of the system. So these pre-calculated buildings are based on two things. First of all, we looked at the existing building stock for the types of buildings, the typologies that we are considering in the project. In the project, we are focusing on office buildings, elderly care facilities, schools, and multifamily residential buildings. But of course, the method can later be extended to other typologies as well. For these buildings, we looked up what are the typical geometrical properties that we see in the stock, and we also looked at the typical configuration and layout of the hybrid GEOTABS system in such buildings, and from that we constructed a parametrized multi-zone archetype model. As you can see, it looks rather simplified compared to an actual building, but the idea is that it's parameterized, and so the geometry can be fitted so that the main geometrical properties such as the shape factor, the volume, the amount of glazing and things like that can be matched to an actual building. So it's a fully multi-zone archetype model that can be simulated and therefore provide relatively detailed information about heating and cooling demands in the building. And we stretch the dimensions basically to match buildings that we observe in the building stock. And for that, we looked at different sources of building stocks. and then selected from the information that we could find on different types of buildings, a big range that covers really the whole range of available properties, so that if your building is not completely eccentric compared to other buildings of the same type, you should be able to find a relatively matching archetype in our database. In addition to geometrical matching of the building, we also looked at typical energy properties or energy-related properties of the building, such as the climate zone is situated in internal gains, thermal mass, envelope performance, shading, things like that. For every geometry, then produced simulations for all possible combinations of these properties, leading to a total stock of buildings that you can select from of about 150,000 buildings at the moment. So all of these buildings have been simulated in an automated way and have been included in the database. And so the database contains full yearly high-resolution demand profiles for heating and cooling for these buildings. And to give you an idea that we indeed cover the whole range of possible designs, this gives you an overview for offices and schools, where you really see that we have fully cooling dominated till fully heating dominated variations of the buildings or each of these typologies in the buildings, in the database. Okay, so that's the first step. We have, so this avoids the fact that you need to do a detailed simulation of your building, because there is a rough equivalent of the building available in the database. It's not exactly the same, but as mentioned before, we are dealing with early design stages, so the equivalence is good enough to be able to proceed at this point. Then we go to the second step, where we do the actual split between the heating and cooling design loads for the taps and the secondary system. So the idea is that if we have a full design load, we assign part of it to the taps, preferably the biggest part, and then the rest is taken up by the secondary system. Because we are in the early design stage and really want to limit the amount of variation that can confuse the outcome, in the design tool, we purely focus on a strict hybrid system, so where the secondary system and the primary system are completely split. As was mentioned earlier, we have hydronic schemes available for more integrated hybrid systems, but that is something that we relegate to the second stage or the later stages of the design process. Because we can assume this split, and we can simplify the actual simulation of the system into a reduced order scheme, as we see here, where the total heating and cooling demand is split between a part for the secondary system that is instantaneous, that interacts directly with the zone temperature, and then a part for the primary system, the GEOTABS system, that interacts with the zone with intermediate latency due to the concrete. And this is very important because, of course, the excitations of the concrete will be attenuated by its thermal mass. And so, as you can see here in this graph, excitations that are too fast basically have no impact on the zone. 100% of it is attenuated, and very slow excitations are not affected by the thermal mass. The typical excitations we have in buildings, however, that have a cycle or time period of a few hours to a day, are heavily affected by the thermal mass and therefore need to be predicted by a controller. And so we mimic a simplified optimal controller, a simplified MPC, where we know what the demand in the future is, and so from that we can predict what would have been the optimal control action in the past to provide us with an optimal result. And by applying this algorithm, we can then, from the desired heating and cooling demand of the space, which is the blue line in this graph, we can obtain what could be delivered by the taps, that is the green dotted line, and what needs to be delivered by the secondary system, the red line, and also, of course, what energy input we need to provide to the taps beforehand to have this output that we need. We can see that this approach really takes advantage of all the properties of the tap system that have been mentioned before. So, for example, here we can see that we will do some preheating, heating the room up more than is necessary to take advantage of the self-regulating effect in the space. And then only in the peak situation here we need some secondary action by the secondary system, because this peak would be too fast to compensate by the taps. It's a simplified optimal control, but still we were able to verify that it provides relatively good estimate of the performance. As you can see here, you get a reasonably close behavior to a real MPC control. And not only is it relatively close, it is also slightly conservative, so which is a good thing to have in an early design stage. So it gives you a bit of a conservative estimate of the performance of the system and therefore also of the sizing. The results in terms of sizing lead to this kind of split, where we assign part of the load to the GEOTABS system, and then the secondary system has a reduced size to cover the peaks. What is interesting to see is that compared to a steady state design situation, we typically find a total design power of the combined system that is substantially lower than the steady state design. And that, of course, since the hybridGEOTABS system is a very investment intensive type of system, and the main cost is in the investment, by reducing the design sizing has a big impact on the total cost of ownership of the system. What we also see is that taking into account, let me go back to my previous slide, an MPC, so an optimal controller, further reduces the needed size of the components compared to a less optimal controller, like a typical relatively simple rule-based controller. And of course, as mentioned earlier, this also further reduces the total cost of ownership of the building. The assumptions on the cost estimates will be covered later by Pascal. So this is the background, let's say, of the design method. I just want to finish by showing some examples of how this then translates into rules of thumb or general observations we see across the pool of buildings that we have simulated. So first, I want to discuss the typical covered by the GEOTABS and their performance. So if we don't look at the geothermal heat exchanger, but purely at what could the taps optimally deliver to the space if they don't need to take into account the fact that there is a need of a yearly balance in the ground, then for 80% of the cases that we simulate, the GEOTABS can cover more, for 75% of the cases, the GEOTABS can cover more than 80% of the total heating and cooling demand of the building. So the potential there is really good. And also in terms of sizing, as I mentioned, we see typically lower sizing compared to steady state calculations, and this lower sizing can amount to up to 70% for the best adapted systems, so the systems with the highest share of hybrid GEOTABS. In terms of environmental impact, this translates into serious reductions of the CO2 emissions for any given building, as was already introduced by Eline, as we can see in our case study buildings. But again, extrapolated to the building stock, we can see that for the large majority of cases, this means that we can reduce the annual CO2 emissions to about 5 kilograms per square meter per year across the different typologies of buildings we are looking at. So we have offices, schools, and elderly care facilities shown here in these graphs. And in terms of CO2 savings compared to a conventional system, this varies between 80, in some cases 90%, and lower numbers for less adapted buildings. Here, taking into account the balance of the grounds. So if we apply other solutions in the hydronic scheme to address the unbalance in the geothermal heat exchanger, and we can achieve very high CO2 reductions in all types of buildings. And to be able to guide you towards a feasible design, even without using the more detailed information from the tool, we are working on these types of decision trees that will be also available on the hybrid GEOTABS website to guide you to the best hybrid GEOTABS solution for your type of building based on a number of high-level properties of the design. So that was my introduction to the design method, and with that, I think we've arrived at the short break list.
Hello, we have indeed. Thank you very much, Jelle. So just because we probably all need a little bit of a break, we'll be looking at about 10 minutes break. So just to make it easy, if we say we'll return at 30 minutes past the hour for wherever anybody is within the world, because I know we've got a few people from various countries, which is great. So we'll see you back at 30 minutes past the hour. We are now going to have a presentation from Pascal Simmons on the hybridGEOTABS design tool. Pascal is project manager at Boydens Engineering, and he became familiar with geothermal and later GEOTABS projects during the evolution of these within the office. And his programming background helps with him assisting on the project on this particular design tool. Over to you, Pascal.
Thank you, Liz, for the introduction. During this presentation, I will give you an insight on the information get from the tool intended to use in an early design stage from your project. Yes, can you give me the next slide, please? Yes, please, Liz. Okay, thanks. The tool shall be available on a web-based format based on 150,000 large pool of cases. Each building was pre-simulated with a variety of different parameters to aim at an intuitive usage in a fast and reliable way. Yeah. Okay, it all starts, of course, with the inputs from the selection of parameters for your project. Hold on, it's not going to the next slide. Yeah. From the project, since the aim is to assist you with the results in an early design phase, the input is very straightforward. No. Oh. Right. Yeah. Okay. First, we'll ask you to give the climate zone where your project is located. For the moment, 3 cities are located in 3 regions. They have been defined as representative, but this could be extended in the future. Also, a study of the current building market stock has provided us with 4 major building typologies, which also has already been addressed. The choice of your typology will differentiate parameters used in the dynamic simulation, as we will see in the next slides. You will have the possibility to choose. Oops, something is going too fast. Yeah. You will have the possibility to choose whether solar shading is present. If you apply it to your criteria, the shading is activated at the solar radiation trigger level of 150 watts per square meter. Okay. You also have 2 major building orientations at your disposal, along with 3 building insulation levels. As for the insulation levels, the first group, the prevailing, and with prevailing I mean the longest facade of your building can be north-south oriented or east-west. And as for the building insulation levels, the first group A is for a very performant insulation level, approximating passive building level. The middle one is an average level, while the third one is a poorly insulated building. Come on. All right. Liz, can you change the slide? I cannot change it anymore, apparently. Yeah, okay, thanks. So for every envelope of your building, you can choose between light or heavy construction type. And by light, I refer to wood type construction, and for heavy, something like bricks or concrete. Okay, we can go to the next slide. Yeah. So as I mentioned before, for every typology, some parameters are different, even though the selection in the tool mentions the same classification. So as you can see here, for high density office, the occupancy is 10 watts per square meter for high density. We've got lighting at 8 watts per square meter, and so on. But for schools, this is different. For example, a classroom has 1 person per 2.5 square meter. We have an occupancy of 30 watts per meter. Lighting is at 8 watts per square meter. There's also a difference for the window-to-wall ratio. Yeah, for schools, low refers to a 20% window-to-wall ratio, medium 40, high 60. For elderly homes, it's 20, 35, and 50. Now, once you have defined all these input parameters, you will submit your criteria for the building that you have introduced in the processing unit. Yeah. And then, okay. Next slide, please, Liz. So this processing unit will give you feedback on a similar building found in the pool of simulated building stocks. The search algorithm is based on the combination of absolute and relative parameters to find the best matching case. As you can see here on the left and the right, you see the result of the parameters of the building which have been found in the building stock, most matching your request. And as for the absolute parameters, we can see that it concerns like low dense, high dense, no shading, insulation level, and for the relative parameters refer to surface, glazing percentage. These are just some examples how it selects your building. Next slide, please. When it has found the most matching building to your input parameters, it first will give you an overview of the dynamic simulation, yeah, on which no splitting algorithm has been applied. The graph on the left bottom will give you the monthly demands on heating and cooling. Yeah, heating is on top, cooling is at the bottom. We will also give you the annual consumption in heating and cooling, absolutely for the whole building and per square meter per year, and also the peak demand in heating and cooling for the whole building and per square meter. Next slide, please. Thanks. So the peak and demand was already touched a bit how it was calculated. So the time series we get from the database have 4 values. So we've got the stationary calculation, which is based on a normative heating loss, heating demand and cooling demand from the building. We've got an ideal predictive control, which was touched in previous presentations as the MPC. We've got an optimized rule-based control referred to as RBC, but also we added in the tool possibility for you to set monthly set points on the core temperature of taps. This gives you an opportunity to actually play with it, and if your building or the building you get from the stock is not completely in balance for the bore field, to play with some parameters and to actually shift some demands from the primary system to the secondary system. Of course, this will not change the results from the ideal predictive control or the optimized rule-based control, but still gives you a possibility, even though it is not optimal or optimized using very smart baseload splitting algorithms, to still be able to implement in a lower share some of the taps in your building. Next slide, please. Yeah, this will result in 3 graphs. Okay, here you can see actually the splitting that was done based on the monthly set points. Yeah. The optimized rule-based control and the predictive control, where the red and the blue parts are actually provided by the taps system. The yellow and gray part is given by the secondary emission system. Now, as you can see, the monthly set points here, as I played with it, it is quite a big part on the secondary system, but as I put the set points in my simulation, you see that there's quite a big imbalance between the heating and cooling demand on the bore field. Because if you estimate the surface of the red bars and the blue bars, you see that the red bars take much more energy than the blue bars. For the optimized rule-based control, which was proposed by this system, you can see that actually the secondary part is much bigger than the primary part, but it tries to achieve a more balanced control. This is not always the case, as I will show you later in the presentation. Some cases actually give us an unbalanced bore field as well in the optimized rule-based control. But as you can see, the ideal predictive control actually reduces as much as possible the secondary production and emission systems and favorizes the complete primary taps system. Next slide, please. Okay. So based on the base load splitting algorithm, which is actually based on the mean of the ideal predictive control, you can see the numbers which are presented in energy use, in primary system, secondary system, cooling primaries, cooling secondary, the energy given by the heat exchanger. And below you get a summary between the base load predictive control splitting algorithm and the monthly set points. As you can see here for the case, the predictive control gave me a bore field balance with an unbalance which is acceptable. The unbalance is limited to 16%, which can still be covered by the regeneration which is done by nature on your bore field. And due to my selection of monthly set points, I managed to get an unbalance in my bore field, which is done by purpose, of course, of 109%. At the bottom, you can also see the hybridity of the solution proposed. This is actually a ratio between the secondary system and the total energy needed for your building. Next slide, please. Then we go to the feasibility study. The feasibility study focuses more on the costs which are needed for the system. Therefore, we got the primary system, which is conceived with the water-water heat pump, the heat exchanger for cooling, and the concrete core activation. The secondary emission system is based on the classic system. The classic system consists of the least expensive system which are on the market. So you get a good difference between the hybrid GEOTABS and its cost, and what the effect would be if you just look at the investment cost of the least expensive, just to compare the two extremes. So the classic system is composed of a condensing gas boiler, an air water chiller, radiators, and a cooling emission system at your choice. I will leave it up to you what is the least expensive emission system for cooling. Next slide, please. So how did we determine the prices to determine the cost of the solution proposed? It's actually a correlation of prices from multiple projects taken from the different participants through the consortium. Yeah. Below you can see the graphs which are used to determine the parameters of the fixed part of the cost and the dynamic part of the cost. We also take into account the inflation of prices, the lifetime of different systems, and we also included PV panels just to cover the electricity needs to compensate for your HVAC system. So the PV panels are not dimensioned for all the electrical needs of your building because we actually don't know them. For for a moment, but only for the HVAC solution proposed. Next slide. So based on these elements, we have created 7 cases. So on the left, you will see the graph, the comparison of the different scenarios on the investment cost. And the right graph is the comparison of the different scenarios for one building on the operational cost. So first, let us focus on the different scenarios. So scenario 0 is based on the dimensioning of your systems on the stationary calculations. So that is based on the stationary calculation of the heat loads and the cooling demands of your building according to the standards normally applied if we start designing a building and doing the calculations. The scenario 1 is the result of the dimensioning of your building or the most comparative building that was found in the building stock based on the dynamic simulation. But here we cover complete demands only on a fossil system, the classical production system. But that gives you, here you can actually see how you can reduce, or how you can see the reduction between if you do a stationary calculation and a dynamic simulation of your building, and you would cover your needs only by a full 100% fossil solution to cover your needs. Case 2 is then based on the splitting algorithm, and here we're going to split the demands based on the ideal predictive control. Yeah, but based, as Jelle mentioned, in the primary and secondary system, that gives you more control on the slow system and the fast system to cover your needs. Where 2B includes the investment for the photovoltaic panels to cover the HVAC electricity needs. Case 3, you can see that this is based on the splitting algorithm on the optimal rule-based control. And then case 4, we actually included this as well, is the 100% GEOTABS solution. Please take into account that this only includes a slow emission system. So as Jelle also mentioned, you should be aware that there could be some comfort issues if you would only implement that system. So you need to actually, as mentioned before, combine it in a hybrid solution to have optimal comfort and optimal electrical demands. So what concerns, if we then take a further look at the operational costs, this is the yearly operational costs. It includes maintenance, energy costs, but not CO2 costs and not the inflation. So it's a first dimensioning of your operational cost. Next slide, please. So if we project this on a 30-year time scale, and we take into account then the lifetimes of your production and energy system, production and emission systems, inflation rate, maintenance costs, increase of energy costs over the years, well, then you get this graph, and you can actually see when a return on investment comparison in the number of years is achieved. Where the middle line is the stationary calculation, the two top ones are based on the predictive control, and the lowest ones are on the on the rule-based control, and the lowest one are on the rule-based control. Next slide. Now what we can do with the tool is actually have the same building As you can see, the surface is the same, the number of floors is the same, the glazing percentage is the same, the region is the same, and the building type is the same. But what I changed is focused in red. I changed the orientation of the building, I changed the insulation level, I changed the shading, I changed the building mass, and I changed the internal loads of the building. Then you can actually see at the bottom what this gives in your annual estimated consumption based on the ideal predictive control, and what it gives you as a result on the monthly set points. We can see that actually for the same building, by just changing those parameters, it can be better, it can be worse, but we see that the annual consumption can be increased by 3. At the very early stage, you can show to your client, by just changing the insulation, what would be the effect on his annual consumption, what would be the effect on the peak demands, but also what would happen if you apply solar shading, or if you change the thermal mass. Even though we are still talking about the same building. Of course, if you would want, you could also simulate by just changing the climatic region, but this doesn't really make sense. You're not gonna advise your customer to put your building in another climatic region. Next slide, please. Okay. So in terms of predictive control and monthly set points, here I have on the left still the same scenario 1, and on the right the second scenario. As you can see, with my choice of input parameters on the left side, I can estimate that the bore field balance due to the total demand in heating and cooling is approximately in balance, also for the monthly set points. But you can see that for the second case, you can see that the heating demand is much higher than the cooling demand, and therefore I have an unbalance. So by playing with the monthly set points, as you can see in the completely right graph, I can improve the bore field balance, even though the predictive control tells me in here I would actually have an unbalance. Of course, the share of the secondary production and emission systems becomes much higher. Below, in the table below, you can see what the impact would be on the investment costs, the operational costs over the 30 years calculated, and you can also see the economy that would be achieved by implementing, for example, if we take a case 2 based on the predictive control, we can see that we have a economy of over the lifetime of 30 years of 324,000 euros based compared to the full fossil solution. Yeah, for the second case, if we compare the predictive control, we can see that we achieve an economy of 442,000 euros based compared to the full fossil control. So you can see, to conclude my presentation, that these results are, you get this feedback quickly from the tool, and if you want to change some parameters, you can recalculate it, and in a matter of minutes, you can see the results. If you change some parameters of your building, what the result will be, and then you can advise your customer to go for one solution or the other, what you find the best. Okay, so this was my presentation. Thank you for your listening to me.
Thank you very much, Pascal. Now, I'm sorry, but I've got some really bad feedback. So the next person who's going to speak. Spiridon, could you take over, please?
Oh, yes. Daniel is going to give the next presentation. And we'll talk about the MPC for HVAC engineers, and goes deeper on the MPC design compared to the last webinar last month. Daniel, the floor is yours. You're muted.
Can you hear me well?
Yes.
Can you see my screen?
Yes.
Okay, welcome everybody to my presentation about model predictive control for HVAC engineer. I will start with simply introducing model predictive control again. It has been described at length during the previous webinar, so I would refer you to the previous webinar for more information, but I would still like to sum up some important aspects of model predictive control. The first thing to know is that model predictive control is an algorithm, and this algorithm, the goal of this algorithm is to control the building ideally, optimally. For that, it contains several blocks. The first block is a model. It contains a model of the building and of its HVAC system, and potentially also of its occupancy or occupancy scale. It also contains weather forecast. And the role of this model is to tell the algorithm what are the future needs of the building and what is the impact of adapting the control on the building needs for energy use or comfort-wise. The second block are constraints, which need to be respected at all times. It can be, for example, comfort constraints, that the temperature is within the bounds, relative humidity, and CO2 concentration. And finally, there is a block which is the objective, and this is the quantification of what needs to be optimized. It can be, for example, minimize the operational cost, or optimize the sustainability of the building, or it can be maximize comfort, or find a trade-off between these things. So the role of the algorithm will be to find where in this graph will be the optimal points, which coincide then with the optimal control actions, still respecting the constraint here pictured by this red line. Once the algorithm has found the optimal control action, it will send it to the building and request some measurement from the building to update the model. This is to avoid mismatch between the actual building and what the model predicts. So that was in really brief what MPC is about, but then the question is, what can MPC control? And that depends on the complexity of it. The most simple MPC will control temperature set points. For example, it will tell what should be the heat pump supply set point, or what should be the ventilation set point, and these are just calculated based on the model and the weather forecast, and thereby replacing a standard heating curve control. But if the model also contains pressure drop calculations, or efficiency as a function of the modulations, or even further, if the model includes the valves and dampers, the MPC can also directly control all these different points. But that will, of course, increase the model complexity. The highest complexity is reached when MPC can even also control the on-off component. And this is complicated because it's a different type of optimization algorithm. If we look at the different MPC that we have developed in the project, there were two types. The first type was developed by Endago Cluster for the School of Leibniz. And there they actually sent set points for the HVAC, so temperature set points, but also pressure set points for the fans, as they included CO2 concentration. The second type of MPC, which was developed by the KU Leuven for these three buildings, were used actually much more complex model, and they could control up to the valve level. Then shortly, one word about the practical implementation. For more details, I would also, again, like to refer to the previous webinar. but how did we install this MPC in this real building? So you have the real building is here with its HVAC system, and the control logic was implemented or is implemented on PLC. And there is also a local computer with an interface for the building management system. We added then in this building a computer connected on the same network as the others, as the PLC, and we were able to send on our control actions and to read the measurement using the protocol BACnet over IP, which was supported by this PLC. We also ensured that we had internet connection to get weather forecasts, send measurement data to database, and to get remote access on this computer. The MPC was then running on this computer and controlling the building. So let's dig now into the main part of this presentation is for HVAC engineers, what should be taken into account in the design to make the building more suitable for MPC. And I would like to start with ventilation, and I hope you will allow me to make some quick and maybe dirty estimation of cost, just to give a bit of feeling at what is at stake. So these numbers are inspired from the Fluvius and Topotri buildings, and we see that they both have a substantial amount of ventilation. The Fluvius 10,000 and Topotri 31,000 cube per hour. Then if we consider typical pressure drops in the ventilation unit and also in the duct system behind it, we can see, and if we assume that the fans are running at nominal power for 12 hours, then we already have for Fluvius about 70 and for Topotri about 310 kilowatt hours per day. Additionally, if it's cold outside, the air will need to be heated up, and assuming that the comfort within the building is 21 degrees and that we have a heat recovery of 70%, we get an additional 200 to 600 kilowatt hours per day. So if we have a ventilation system working at nominal condition for 250 days per year, and that we assume that we have about 80 days of heating, and that electricity is 10 cents and all the heat is produced by heat pump, we get numbers as high as 2,000 up to 9,000 euros per year. So these are substantial, and how can we reduce this cost? Simply by reducing the ventilation flow. But for that, we need modulating fans, which are, I think, most of the time included. But we also need CIVs for the different zones with variable occupancy and CIV for other zones. Because by doing so, we can firstly decrease the flow for these different zones, but we can also decrease the pressure head of the fans. So we have two ways to actually reduce the ventilation power. In case for MPC of Fluvius, we were able to save up to 60% sometimes for the ventilation. These are significant numbers. Obviously, for this, we also need sensors to be able to measure the CO2 and the CO2 concentration and the temperature per zone to ensure that comfort is still granted. There are also a few points to take into account for the hydraulics. And let me start with pumps, because for hybrid GEOTABS system, the pump power may be significant. So again, if we take some numbers from Fluvius and Topotri, we had a pressure drop of between, let's say, 1 and 2 bars in the bore field plus the heat pump and the passive heat exchanger, and we had significant flow rate in this. So if we consider a pump running full powers 24 hours per day, because it's not modulating and because it's not cleverly controlled, and this for 200 days a year, because it's both for heating and cooling, then we would end up with rather high numbers, such as 700 to 1,500 euros per year. What's important is to install modulating pump for that. A simple controller, as it is implemented in this building, is to use a PI controller to make sure that the temperature difference on the bore field is constant, and thereby varying the flow according to the power. We'll already be able to save most of the energy, but MPC is going to be able to go further than that by actually optimizing the pressure head of the pump, taking into account the impact on the temperature by doing so. second aspect, which is important to take into account, and this is also a general guideline for MPC, is that we need a higher degree of freedom. The more freedom MPC has, the more optimally it will be able to behave. So when we have taps, if we have, for example, north zones and south zones with different energy or different heating and cooling needs, it's interesting to separate them into two different circuits and to enable recirculations of the return water so that we can have different supply temperature for each circuit, such that we can provide different amount of heat or cold for different zones. You can go even further than that by also including two-way valves for the sub-circuit, such that, for example, you can close the circuit of the middle floor of a building as that floor doesn't need any heat anymore, while the ground floor or the last floor would stay open. So in general, try to be able to control the different taps circuits as well as possible, because MPC will really make use of that. You may also have in your building some zones which are warm while others are cold, so you need simultaneous heating and cooling. And there it's very interesting to make it possible to recirculate the water from one zone to the other, because MPC is going to see that and potentially be able to prevent using the heat pump just by recirculating the water from one zone to the other. Then the previous speakers have already emphasized the importance of the interest of having hybrid systems with both slow system and fast system. And MPC is going to be able to use this. For example, on a sunny day at lunchtime, the building might need cooling, while in the morning after the night, it might need some heating. So MPC might want to use the fast system just to give the necessary amount of heat to reach comfort early in the morning without loading the taps, so to avoid overheating at lunchtime. But to make that possible, it is important that MPC can control both the slow and the fast system centrally. So if your fast system are radiators with thermostatic valve, which is only manually controllable, you will hamper your MPC and actually not allow it to use your fast system, which is a pity in the sense of optimality. So besides these hydraulic changes, I would also like to mention some points about sensors. I see that there is an increasing number of sensors in buildings being installed, but not always the sensors we need. A very important type of sensors we need are sensors for zones to measure the comfort. While? Because MPC will try to find the optimal point. That means the point where comfort is reached, but energy is as low as possible, or objective is as low as possible. And this is often just at the comfort boundary, which means that it needs to have a good feedback from the real building to the model to make sure that there is no offset there, that the model is not 2 degrees off. Otherwise, you will cause discomfort. But it's also simply important to have these sensors to be able to evaluate the comfort through the year in the building to ensure that the system is working well, regardless of the type of control it's installed. For the hydraulics, it's of course important to have several temperature sensors within the circuits to be able to check the system, but it is mostly the case as installer needs that too to make sure that the system is working properly. But besides that, it's interesting to install a few calorimeters just to know what are the different energy flows. So for example, 1 calorimeter for the taps, 1 for the radiators, 1 for the ventilations. That gives a feeling at where is most of the energy going, and it helps to find mistakes in the system or simply to know what should be firstly optimized. But the problem is that in most of the building I've seen, the calorimeters were either not properly installed or not properly connected to the BMS system. And so they are not so reliable, unfortunately, and I'm not sure exactly why. But what type of sensors which are reliable are electricity counters. I would definitely advise you to place a few ones. For example, 1 for the total HVAC system, 1 for the ventilation, 1 for the heat pump system, and similarly, a gas counter as well. These sensors will provide you Then I would also like to say something about the building management system. In this area of Internet of IoT and of remote access, it's surprising that actually getting remote access of BMS is still very challenging. And this is because most of the time BMS are installed on the local network of the company, which would then lead to a security issue to get access to third parties. But there exist many different solutions for that. And I think it's important for designers to include these specifications into the BMS system, into the specs, to make sure that everybody has access to BMS who needs to have access to it. Another painful point that we discovered during the project is that it's the different measurement points and control points don't have a unique identifier. So there's a different identifier in the BMS than on the backnet layer, than on the database. So it's a whole puzzle to find out which point is which. Therefore, it's important to create IO list, and ideally this list would also be visible on the hydraulic schemes, and that installer are obliged to implement that into both the BMS, the backnet, and the database. It's important to use open protocol. You have seen at the beginning of the presentation that thanks to the fact that the BMS supported backnet, it was fairly easy for us to connect to the machines by simply bringing a computer on site and communicating through backnet. If you use a proprietary protocol or a closed protocol, this is not going to be possible. This leads me to the next part of this presentation. When it's actually interesting to consider MPC in your building? And I'm going to do this fairly shortly. And there are a few interesting points, a few interesting aspects where MPC will be a good solution. So as mentioned earlier, if your building has a slow system, tabs or large storage, means that the building also has quite some inertia. It's interesting to have a control which is able to foresee what will be the future needs and act accordingly. What's also interesting for MPC is if the building has a hybrid system. So there is always a trade-off to choose between systems. For example, at the production side, use a heat pump or the gas boiler or air-to-water heat pump. They all have different efficiencies at different times. So MPC will be able to find which one to use ideally. At the emission side, again, there's taps, which are slow but cheap, but there's then a faster system, such as ventilation. MPC will there make the best choice between them. As mentioned earlier, also, if you have simultaneous heating and cooling demand in the building, MPC might be able to bring the energy from one side to the other side, and thereby avoiding to actually have to create that energy using electricity or gas. Variable electricity price is definitely a main added value of MPC, which is going to be of increasing interest. So if the building has inertia, MPC should be able to shift the loads to low cost moments. And finally, if you have a highly modulating system, so many degrees of freedom with variable efficiency, MPC might also be an interesting candidate. What's not interesting for MPC is if you have a very narrow comfort bounds. So if your room needs to be always between 21 and 22 degrees, for example, then there is not many degrees of freedom, and then MPC will not make a big difference. Another thing is that if there is no control on the system, so remember radiators with thermostatic valves, that's not going to be interesting for MPC as it cannot control it. Then you may have the question about, imagine you know that MPC will be installed in the building, then should you size the components differently? And the answer is a yes and no answer. Firstly, MPC is very good at predicting the need of the building, so reheating factors could be avoided. So reheating factors is, for example, that you have a room that you add an additional power to your system, such that the room, for example, can be reheated in 30 minutes. but MPC will be able to anticipate how long it takes to heat up the room and therefore start on time. So I would advise that reheating factors would be avoided. Also simultaneity factors. So if you have one zone, different zones in the building which are not used at the same time, MPC will also be able to detect that and avoid that all the systems are running at full power at the same time. But what you should not do is to downsize the system capacity of your total building, as MPC is not yet a market mature technology. So with that, I mean that on the coldest day, -8 degrees, you may still not need so much power if your building was being heated up full power for 3 days in advance. But this is, I think, yet too much of a risk to take that into account. We first need to see numbers of robust MPC implementation. I would like now to wrap up with really preliminary results. At the end of the project, we'll provide a full detailed analysis of this, but I think it's still interesting to have a look here. So it's a period of 3 weeks from the 17th of May 2020 to the 5th of June. And you can see at the top the top two graphs are the temperature of the different zones. And on the third graph here, the concentration. And on the bottom here, you can see when MPC was off, so the original control, and when MPC was on. The blue line is the daily average outdoor temperature. The first thing that we can see here quickly is that there is not really a comfort difference between the MPC period and RBC period. They were both able to stay within the bounds. And if we look at the energy, what happens with MPC and without MPC, so let me first explain the graph. In the box plot that you can see here is the total energy used in 2019 of all the days which are the same daily outdoor temperature as today, as this day, so the 18th of May. And the red one is the actual energy used on that day. So we can see that when MPC is not on, that the actual energy used is similar to the one from the year 2019 at the same outdoor temperature. But when MPC is turned on, we can see here that there is a significant drop of energy use compared to the previous, to the year 2019. So this is for the total HVAC use. This is for the heat pump electricity use. So you can see that during this period, MPC was able to significantly drop the energy use of the heat pump. And finally, ventilation here. You can see the ventilation energy use again that MPC was saving quite a lot there. This is only a period of 3 weeks, but we have looked at also winter period and summer period, and graphs were similar. But the actual quantification should wait till the end of the project. With this, I would like to thank you all, especially Buildings Engineering, to make it possible for us to implement MPC in a few of the buildings they have designed. Also, Priva for the help on getting access to the machine and the control. If you have any questions about the potential commercialization of the white box MPC in buildings and the spin-off which is being created, you may contact me or some of my colleagues. And if you have questions for the commercialization of the gray box MPC, you may contact Jerry Sickliffe. Thank you very much.
Thank you, Damien. Oh, that's good. I can hear me again. So now we'll go on to the question and answers section, which Eileen Himp will be managing. We've had lots of questions, so it'll be interesting to discuss. Thank you.
Yeah, hello. I would like to ask to all the presenters today to turn on their cameras so we can see you. And then I have a question to the public. Please, if you have any questions to the panelists about what you have seen today or about hybrid geotabs in general, you can still add your questions into the question and answer chat, that window that you can see. So you're very welcome to add additional questions. From the questions that have been asked before today, quite a lot of answers have been foreseen in the chat, but I'll pick some of them out and ask the panelists to respond to them. I may start with the two practical questions about the web tool. First one is a question for Wim Boydens. Or I'll start with a question for Pascal Simons then. There's a question of whether the database of demand profile that is available in the tool, so the tool is using very detailed energy demand profiles of heating and cooling loads at hourly time step. Is this possible to download it from the tool? Is it possible to do that? Pascal, you're muted. Thank you.
Okay.
Yeah.
Yeah. Okay. So the database with the 150,000 cases is for the moment stored in a data center, not in Europe. But the size of the database is almost 400 gigabytes. So it is not possible in a decent manner to download the database, and this is why the tool was created. So actually the tool is a server-side analysis tool to be able, which is also implemented on the servers in the data center, to have a quick information interchange between the analysis tool and the database. Just to give you an idea, the time series, if you know that there is 8,760 hours per year on 150,000 cases, this makes an enormous, huge table, and it would take enormous amount of time to download it. So this is why we actually implemented the web interface, to be able for you to access everything in decent time. In a decent time. I hope this answers a bit the question about the complexity of the database and the interface to the users.
Thank you, Pascal. Over to Wim. I'm sorry, Wim, I couldn't see you, but it's all my mistake. So question for Wim Boydens. There's a question whether we can expect hotels to be added to the database as building typology. Please unmute yourself. Oh, sorry. Okay. I'll give that question to Jelle Lavesche then. Also unmute yourself.
Yeah.
Okay.
So yes, it's not available now. It's as was mentioned before, the main typologies we're focusing on in the project are schools, office buildings, elderly care facilities, and multi-family residential buildings. We hope through the knowledge center that has been announced by Wim also during the presentation to be able to continue to work on the tool and the database in the future, and then extending the scope of typologies and buildings that are available in the tool is one of the main goals.
Thank you. Then there are a number of questions with interest related to the control of hybrid GEOTABS systems. There's a lot of questions on how to make sure that these different systems work together nicely and how that's done. I'll pick out first a question that is more related to the rule-based type of control, where a general question is now how to prevent that a secondary system takes over. Wim Boydens, could you try to speak again that it works right now? But it still doesn't work. Then I would like to give the chance to Damien Picard to reply.
Yes, thank you. Can you hear me?
Yes, thank you.
Okay. So as Lambertus has mentioned, a first important point is that the taps typically not use a feedback mechanism on the zone temperature. So the set point of taps will depend on the zone temperature, while the pass system will depend on that. There is not really a conflict there because you will need to tune your taps well so that you are within the point, and your secondary system should only jump in if you get outside the bound. You could add additional safety mechanisms such that the taps is in heating mode, for example, you do not want your secondary system to be in cooling mode so that you do not destroy temperature. And you don't really have a complete competition there. Does that answer the question?
I believe it does. If not, I suppose you'll ask additional questions in the chat right now. Then I'll stay with you, Danya, with another question then related to model predictive controls. As you have explained, it's probably a much more suitable control to tackle the issue or the difficulties of hybrid geotap systems. But is the MPC available as a standard unit, or is it something that really needs to be developed project by project? How is the status today, and what is expected in the future?
So firstly, it's important to realize that there are different types of NPCs. There are NPCs which are based on measurement data. Think of, for example, the famous Nest thermostat from Google, so which do not require physical parameters of the building. It's just going to measure and try to learn from the measurement how the building acts. So in that case, MPC is fairly general, it could be applied to any building, but of course, it always requires some tailor adaptations, such as knowing which type of sensors are available, which one are reliable, what do they stand for, and so on. Then there are certain MPCs, the one that Evan has developed, which contain a full physical model of the building. And there, the framework is general, but of course, you will need to apply it to your given building. But we are creating tools to be able to input all this information on a very quick manner. For example, tools to draw roughly the buildings and their zones quickly, then to be able to define which type of HVAC systems are available per zone. Actually, something a little bit similar to what the control companies are currently doing with their own control. So a modular approach. So to wrap up, I think the MPC developed in these projects are obviously applicable to most of the building types, and that it will require a manual setup for a building.
Okay, thank you, Daniel. Then I'll have a few design related questions that came in. One of them being, what can hybrid geotapes do for me when I have a heavily heating or cooling dominated building? I again wanted to ask this to Wilbert. Yes, this time you can. Okay, welcome again. So please, what to do with heating or cooling, heavily heating or cooling dominated buildings?
Actually, the approach is you have two main parts for the approach. You could either say, I'm very unlucky, I have a heavily cooling dominated building, and then the share of taps or GEOTABS that you take into account, you limit it to a degree where the balance is reached. And of course, then you have a smaller bore field. Or you could say, no, I will not do that because I have possibilities to regenerate my bore field and to create the balance with a secondary system, for example, the thermal solar panels that reheat the building and then the more warmer periods, sunny periods, could be the end of September or the end of August, depending on the region where you are. Or cooling down the bore field with a cooling tower that works when the outdoor conditions enable this to do it in a very cost-efficient or energy-efficient way. So actually regenerating on a renewable basis with what is available in the surroundings of the building or the climate at a different time of year in order to have it as environmentally and cost-friendly as possible.
Thank you. I would also like to give you the chance to, if there were any further comments you wanted to give to the previous questions, to give you the chance to do so. I don't know if there were any comments you wanted to give to the future developments in the tool.
Was this a general question, Eileen?
Well, specifically for hotels, but
yeah. Well, as you will see, there's a lot of possibilities, either on the building types. Of course, for a hotel, we should first ask ourselves, what are the merits? We're working on hybrid GEOTABS, so in the first place, we should look at how good would this be. So we didn't look at it in the project. So that means it would be a first elaboration of what is the potential, and secondly, what is the total energy use in the European Union or on other continents for hotels. So do we make a difference there? Of course, in a hotel, I told you about the room by room set point change, that the taps is not handling what the secondary system is. And of course, in a hotel, if you have a lot of changes, and that's typically a hotel operation, well, you can feel that the potential is much lower. So the taps it could be for a very successful hotel chain that knows they're occupied 80% of the year, then it's good. But if you have a lot of variations, then maybe potential would be smaller. So yes, it can be done, but I think we have other typologies of buildings that we can approach first and also include in the tool. And then secondly, of course, because all designers, they would like, I think, probably more geographical cities where they could make an assessment on. Not only for the climate, but also because we have a whole variety of energy prices, a whole variety of CO2 taxations, and actually, the further we go in this transition, the more detail still is needed to really assess in Poland, do I have a good case here, yes or no, more depending on policies than on building physics. So I think there's a lot of potential work that we could do, and we will if we see that there's enough interest in it, so that we can provide or ask the resources to enrich the tool itself. Okay, so it should be a common approach based on the questions from the market, the questions from policy regions in Europe, and then but we have the expertise together, and expertise can always be joined by others. I think once this movement enriches and broadens the methodology that we have applied.
Okay, thank you, Wim. One final question for you. It's based on some of the questions in the chat. Discussing, you presented today that dependence on the ratio between gas and electricity prices in our countries, GEOTABS may be a more or less interesting solution from financial point of view. But what about the future? Thinking of in Europe then the Green Deal and the future evolution of our energy systems, what are the main benefits of hybrid GEOTABS to use it in the future energy system in the coming 10, 20 years?
Well, I think you're asking me for a wrap-up about many things that we have talked about. If you look at the future, and I look from the customer side, it's clear if you have variable prices, Damien also mentioned, then there's a big win, financial win, to have something with such a flexibility. If you look a little bit deeper towards the energy system behind it, and you think that, or you believe, or you help to make our energy system less and less carbon intensive, then you also know that the intermittency of the renewable electricity on the grid, you can use it. You're not only looking at the price then, but also at a societal challenge that is easier to meet. And of course, it looks like I'm only looking at the taps now. No, I think that the seasonal storage in the ground is quite an important issue. It's an important issue because it's not competed yet, and I don't think in the following decade, by an electricity storage, even not by hydrogen storage. I think this will need time, and this solution is there. It's proven, it's ready to implement and ready to deploy. And we don't have the time in the whole energy transition to let us wait for 10 or 15 years. So it's a good possibility or a good solution to implement seasonal storage. And I think that's a big value. And I had one other thing in my mind, but it slipped my mind again, even though it was very important. Yeah, let's not wait. That's the message. Let's go on with the proven solution.
Thank you. A question for Jarela Verschuda. There was a question about applying hybrid geotabs in renovation scenarios. We can talk about the supply side, but what about the building side? The building design for in case of buildings and renovations, how would hybrid geotabs relate to your building design?
Yeah, so, well, there's two sides to that question. Of course, the first one is how to implement TAPs or TAPs-like emission systems in an existing building. So if there are no TAPs-like systems such as underfloor heating available, one of the partners in the project, namely DTU, together with Uponor, has been working to develop a retrofit solution, which is a phase change material-based ceiling panel that can be used as an analogous emission element, and so it's very lightweight and can be retrofitted in existing buildings. And then the other side of the question is, okay, what type of buildings could benefit from TAPs? I think the analysis that we are doing on the impact of selecting GEOTABS on potential buildings with different properties shows that our baseline of our project and every building deserves a share of GEOTABS is really true. And so for any existing building, there will be, if it is feasible to retrofit it with TAPs-like emission and to implement a geothermal heat exchanger, there will be a share of the loads that can be covered by GEOTABS and to help reduce the emissions of the system. And the tool can also be used to estimate that.
Thank you, Jelle. I'll pass on to Wim, who wants to add something on this.
Yes, and it combines a little bit the question or the thing I forgot and the thing that Jelle said. That of course in existing buildings where for some it will be feasible to really go into depth with renovation, for others it will not be. But as we look towards the future, we know that we'll have more need for cooling in high temperature summers. And if we have projects, the buildings that we are building now are more and more performant, so they are future ready. But on the other hand, you could say that in a ground source, so in a bore field, we could try to combine all buildings in the neighborhood with the new projects and try to reach a balance there so that you win on multiple sides. The comfort, of course, in those old buildings in high temperature summers. you combine them together to get a more collective approach of the ground balance. And okay, even if there are two different typologies, you create a win-win for those two buildings. So the new buildings that we built due to EPBD in Europe, they're becoming heavily cooling dominated, while 10 years ago this was impossible in Central and Northern Europe. So this is a challenge, but this is an opportunity for a system like the geothermal and the GEOTABS as well. So if you combine them with other buildings that need more heat and are happy to have some cold in summertime, so it makes an interesting exercise to go towards clusters and not each building individually.
Thank you. Then there's a practical question. Is the tool publicly available and where can we find it? An important question. Pascal, would you like to react?
Well, we're actually finalizing and securing the website. So by the end of the period on which this project will finish, it will be made publicly available on the website and accessible through the website of hybridGEOTABS. So in the very near future, beginning of next year, it will be available.
At this moment, it has been tested out by our own project partners to make sure that there are no bugs and problems in there anymore. And so the project ends by end of February 2021. So at the latest by then, it will be available via hybridGEOTABS.eu. And then there's a question about whether there's any data sheets or technical specification about how to size taps. Pipe diameter, spacing, installation info in general. What I can reply already to that is that this course that has been taken place today is part of a larger curriculum of trainings that are available via webinars for designers. And one of those trainings that took place about a year ago was about the detailed design of taps, the detailed design of heat pumps and of geothermal bore fields, where there is more information on how taps are made, what are different sorts of taps, also high performance taps, what are the diameters, and all this sort of information. All these trainings, including the one from today, will become available in a full curriculum that you can follow via YouTube. But all of this information will also become available in the next 2 months via the project website, which is the place to go, your one-stop shop to find all directions to all the dissemination material. I think that's more or less all the questions we got from you today, and we're very close to the end of this seminar. So I will give the floor back to Liz Elston to close off this session.
Thank you, Elaine. Is it possible to share my screen, please, Spiridon? Thank you.
You're the presenter. Yep.
So today we've had some really interesting presentations from all our speakers, and as Elaine has mentioned, there are other additional curriculum modules that we've presented or provided, and we'll put those all together. But there's been some really, really interesting questions, and thank you everybody who's attended. I can see that we've had people from all over the place of Europe, the UK, Iran, and other countries. So this is fantastic that the word's getting around and we're sharing, and we've got these possible collaborations and opportunities for future discussions. I just wanted to highlight some more aspects of our GEOTABS, hybrid GEOTABS activities during this project. We've been looking at enhanced geothermal response testing, cost, benefit and analysis, and a policy report. We also have the hydraulic schemes which were mentioned available to download on the website already on the technology page. So please have a look at those. Jelle had mentioned as well and answered the question about what we can do to refurb existing buildings potentially with the PCM panels for radiant heating and cooling. We also have an energy dashboard for all the case study buildings, which is also again accessible on the website with the case studies section. And at the moment we're putting together a hybrid GEOTABS manual, and this is almost ready for publication. Again, this will be the beginning of next year. And on top of that, hopefully the web tool as well. And we'll also have all of this training up on our YouTube channel alongside the slides as PDFs within the publications and presentations section of our website. So big thanks to everybody, and also a huge thanks to all the speakers and all their time and effort today. This is our contacts list, and we're on LinkedIn with a showcase page, which is great to follow because there's various information and news popping up on there regularly. We have a LinkedIn group as well for discussions, Facebook page, Twitter, and also we've just been implementing an Instagram, which has managed to contact quite a few people from various areas of the world again. And there's also the link to our YouTube channel, which has also got some information and explanatory videos about what is hybrid GEOTABS and personal responses and feedback from residents within the buildings or occupants in the buildings as to comfort and energy savings. So please do go and have a look at those. And there's our email for contact and our website if you want to actually also sign up to our mailing list. Thank you. And so I guess we'll wrap this up, and I just want to say thank you to all, and hopefully you'll be able to find the information, but if you have any questions, please do contact us. Thank you.